Hi everybody, welcome to a quick video about coordinate systems. So what are coordinate systems and why are they important in GIS? Well, one motivating question is to just ask, how would you describe your location to someone? And of course, we all know we would use latitude and longitude. So 44 degrees north, 72 degrees west, for example. But when we think about coordinate systems, we need to think about what is that latitude and longitude referenced to, and how was that grid established? And moreover, how do you actually know what your latitude and longitude are, especially if you don't have a GPS in hand? Well, of course, in the pre-GPS days, you would read that from a map. And map makers knew latitude and longitude relative to a bunch of benchmarks of known locations. So in this video, we'll go through a little bit about how this lat-long grid is established, what the role of the benchmarks is, and how coordinate systems have changed over time. So most coordinate systems have four parts: an ellipsoid, a geographic coordinate system, a datum, and then sometimes a projected coordinate system. So we'll look at each of these in turn. So if you want to break Earth into a grid of lat-long, the first thing you do is you have to decide what the surface of Earth looks like and agree on that shape. And that's done using what's called a reference ellipsoid, which defines the major and minor axis of Earth. And the ellipsoid is basically defined by the geoid. The geoid is an imaginary surface of gravity equipotential. So it's a surface of constant gravity. And gravity, of course, depends on topography. And then the ellipsoid is simply the average of that geoid in most cases. So now that we know the size and shape of Earth, how do we break it into an evenly spaced grid? Of course, this is done with lines of latitude and longitude. But like any grid or coordinate system, the origin needs to be defined. In this case, the origin of this grid is given by the intersection of the Greenwich meridian, which runs through Greenwich, England, and is a line of 0 longitude, and where that intersects the equator, which is defined as 0 degrees latitude. And so this is really the 0 point of the global coordinate system. But from there we have an even thornier problem, which is, in the old days, surveying is required to actually then determine where exactly each of these lines of latitude and longitude fall on Earth. It's easy to draw this in a cartoon representation, but to actually put your finger on the exact spot where 22.5 degrees longitude is a lot trickier. In part because it basically has to be all measured relative to, for example, the origin or to some other known point, like Greenwich, England. So the way this is done is using datums, and datums are networks of benchmarks that have a known latitude and longitude. So in the early days of surveying, hundreds of thousands of man-hours were spent surveying the actual distance between points and actually pounding in benchmarks into rock such that the actual latitude and longitude of that point would be known. And then any subsequent surveys could be done off of that particular benchmark, which had a known latitude and longitude. So that worked well, and datums gave us the ability to kind of draw out or lay out the lat-long grid. But of course, over time, surveying techniques improve, and it may be that the early surveys weren't exactly right. Maybe they were off by 5, 10, 20 meters. So in the subsequent years, new datums have been introduced. And if you look at a list of datums, you'll find dozens of them. Two of the most common datums are WGS 84 and NAD 83. So these are two that are really commonly used global datums in GIS. So how different are these datum shifts when people redo the surveying. A good example is the shift from the North American datum, NAD 83, versus the original NAD 27. So we can see that the difference is about 20 meters if you're in the Midwest. It's up to 100 meters if you're out in California. That may actually be in feet, I'm not positive. But the key point is that the benchmarks themselves didn't move. The surveying was simply redone, and it was determined that that benchmark wasn't actually at its original Latin long. It was actually 40 feet off of where it was thought to be before. So kind of just refining this latitude and longitude grid. But what's critically important is that whenever you determine your latitude and longitude today, say with a GPS, it's being determined relative to a datum. So you're basically saying, look, I'm someplace on Earth. I have to describe that with a latitude and longitude number. And that lat-lon number has to be relative to a datum. So you always have to specify which datum you are locating yourself relative to. And that's why it's so critical not to confuse these. You have to always specify that. If you get it wrong, you're going to be off by this much, 20 feet, 100 feet, etc. So we've talked now basically about geographic coordinate systems, datums, relative position. Let's finish up by talking about projected coordinate systems. And this is a bit of a problem because the coordinate system we described before, the Latin long lines, were basically circles. They were circles that were transcribing the sphere that we live on. But most of the way we view maps is actually on a flat surface. So we're effectively always trying to view a curved surface of the Earth on a flat map projection. And a simple way to think about this is, if this is Earth, and if you're trying to draw a map of Earth on a flat surface, you effectively have to unwrap this circular surface and spread it onto a flat surface. Now, mathematically, the way this is done is with a projection. And we can visualize that by basically, in this case, it's a gnomic projection. So we can imagine a point of light in the inside of the Earth, and with those rays of light or vectors going through the surface and then intersecting a plane out here. And so this point on the surface of Earth gets projected to this point on the map, this point to this one, and this point to this one. So what we see is that depending where the plane is relative to the sphere, points will, their linear distances apart will not be preserved in the projection. So we can see that example here. If this is the plane we're trying to project onto here, and we've got 4 points on the sphere, A, B, D, and E, we can see that points B and D end up getting projected, so they end up further apart than they are in reality, whereas points A and B end up getting projected so they're actually closer together than they are in reality. So depending on the projection relationships, those distances and areas are not preserved during the act of projection onto a flat surface. Now, to minimize the warping effect, it's best to have the surface upon which you're projecting most closely approximate the circular surface. And there's a lot of tricky ways to do this, and there's a lot of different types of projections. In this video, we're only going to talk about transverse Mercator projections. And the way this typically works is there's a sphere, Earth, and we fit that sphere inside of a cylindrical tube. Okay, so Earth is a ball that's been slid into this tube. And again, it's a projection from the inside of the ball out to the surface of the tube. And there's one point of contact running up and down a line of longitude, or the central meridian of Earth. And then to convert it into a flat map, we would slice this tube and unroll it into a flat surface. Okay, so first we do the projection, then we slice the tube and unroll it. The result, of course, is that the part along the meridian that actually was directly touching the inside of the tube is not distorted at all. There was no movement or distortion between where the point was on the sphere and where it comes out on the unrolled cylinder. But any place off of that meridian, over in this area or over here, is a bit distorted. And this map attempts to show that distortion. If you imagine these circles were roughly this size to begin with, and those circles were roughly that size on the spherical surface, they've now been blown up to be that big on the edges, or they've been shrunken and elongated if you're up near the poles. So the main point here is that these circles represent a shape, the relative locations of a bunch of points that enclose an area. And the relative locations are distorted in the projection. The shape gets bigger, the points get further away. And all projections have that problem of distorting the geometric relationships as you go from a circular surface to a flat surface. So one other common Mercator projection is a state plane coordinate system. And what this does is it gets around the problem. You can see when we try to project the whole Earth onto a single projection, obviously the Earth doesn't really approximate a flat surface at all. So we end up with terrible distortion. State plane gets around that by using a series of much smaller footprint projections. So each state might have one or several or many actual individual meridians. And the idea is that the plane of projection actually pretty closely approximates the flat surface. And by using smaller footprint areas, you don't really have to deal with the curvature of the Earth, or the effect of the Earth's curvature is greatly minimized. So this is a huge advantage because the distortion is very, very limited, and you don't have to worry too much about distortion of geometric relationships. The disadvantage is that it's a small footprint. It's only relevant to data in this part of Minnesota in this case, and it won't work sensibly with a global data set. The most common transverse Mercator projection is called the Universal Transverse Mercator, or UTM. And this is basically a series of 60 different Mercator projections. Each one has a central meridian that is basically a line of longitude, so it runs north to south in this case. And we know that there should be almost no distortion in the transverse Mercator projection along this line of longitude, right? We know we can unwrap that, and that particular line has no distortion. So the idea of the UTM coordinate system is that you've got a whole series of lines, and then each one is kind of narrow, has a narrow width, so that you encounter less distortion because you're moving only a limited distance away laterally. So again, this system works very well. It's a global system. The only drawback to it is that you have to always specify which UTM zone you're in. So you have to always, any coordinates have to be referenced to this central meridian of a given UTM zone. So here's a map of the United States. We span 9 of these UTM zones, 10 to 19. Vermont is in zone 18N here. And so let's look at how the actual coordinates are given in a UTM system. So first off, the coordinates are always in meters. They're not in degrees. Now, the origin of this coordinate system is defined as 0 meters, 0 meters. And each UTM zone has an arbitrary origin. In this case, it's defined actually outside of the UTM zone, someplace off to the west of the UTM zone. So in terms of east-west coordinates, 0 is at that origin, And then the central meridian of the zone is always at 500,000. Okay? So it's always going to be at 500,000, this central meridian. So the easting coordinate, or the east-west coordinate in here, is going to be some number in the hundreds of thousands. And it's always going to be positive. Now when we think about the northern coordinate, the origin is always at the equator. So it's 0 at the equator. And positive numbers go up to the north, and positive numbers also go up to the south. So you'd go from 0 up to 4,900,000 in the north direction, and you could also go positive in the south direction. So the kicker there is that in addition to defining your UTM zone number, like 11, you also have to say whether you're in the north or south zone. And that's what's going to tell you whether you want to be counting positively to the north or counting positively down to the south. So in that case, both your easting and your northing are always positive numbers, and you're always counting from some false origin. UTM zones, of course, also have the added benefit that you're already working in units of meters, which are super intuitive and easy to use in measurements, instead of degrees, which really are only useful when you're talking about angles. So meters are a great unit for actual life, but most coordinates are in degrees. So let's wrap this up. Why do projections matter? Who cares? Well, a couple reasons. One, your computer screen is actually showing a projection. It is a flat screen, and it's trying to show you something that is circular. So anytime you're envisioning data, it's being projected into something flat that you can see. And if you happen to be looking at two different images and two different projections that you're overlying, they may not overlap correctly if you have them in different projections. So a point on one might not match the point that is showing to be directly beneath it. Now in ArcMap, it usually projects data on the fly. So in fact, even if your data are in different projections, you're usually going to see them correctly rendered on your screen. And a final reason projections are super important is for any kind of spatial calculation. Keep in mind that when you project things, they get distorted. So if you measure a distance on a projected image, it might be wrong, because what you really want is the distance on that curved surface. So it's important to use projections that minimize distortion, so that if you measure a distance on a flat surface, it's pretty close to the same answer as what you'd get on a curved surface. So anytime you're doing calculations of area or distance, you want to be really careful about what projections you're using. Now, of course, just a little advice about ArcMap. Every layer that you load into ArcMap has some native coordinate system. Sometimes this will be projected already, sometimes it will be unprojected. Now, the Arc project itself also has a coordinate system, which usually is taken from the first data layer that you load. It usually adopts that coordinate system. And it's very important that all the layers have the same coordinate system in your ArcMap project. It may not matter a lot for display, but it matters a lot if you start to do calculations where you're extracting values from things or computing areas of things. So keep that in mind going forward. The end. Thanks for listening, everybody.